Video Manuals presents Stroker number 1, the bottom end. Here we have a typical Harley Davidson 5-piece counterweight crankshaft for a 1340cc motor. It is interesting to note that Harley Davidson uses this style of crankshaft in all their motors. The shaft facing towards you is the sprocket shaft and is the primary side or left-hand side of our motor. Immediately above the sprocket shaft, we have the first of two crank pin nuts. The shaft to the right of your screen is the pinion shaft, and this is the cone side or the right-hand side of our motor. Directly above the pinion shaft, we find the second crank pin nut. This is where we stopped in the disassembly on both the shovel head and the Evolution motor overhaul video manuals, with the crankshaft assembly still mounted in the sprocket side or left-hand crankcase. To remove the crankshaft assembly from the primary side gear case, we place the whole assembly in our press. Using a pair of parallels, we support the crankcase on both sides, making sure that we have as much of the crankcase supported by both parallels as possible. The flywheels must have enough room to travel a couple of inches to the table, allowing the crankshaft assembly to move completely out of the crankcase. We only allow a couple of inches so that the crankshaft assembly will not crash into the table of the press when it finally breaks free of the crankcase housing. We place a small aluminum arbor on the end of the sprocket shaft and start to slowly press the crankshaft assembly out of the crankcase. We constantly check that the flywheels are clearing the two parallels. Now that the whole crankshaft assembly is resting on the table, we carefully lift the crankcase until it clears the sprocket shaft. To remove the Timken outer bearing races, we use a split mandrel consisting of one arbor and two sleeves. We're going to press out the bottom race first. The lip of the sleeve is placed here against the snap ring in between the two outer races. The lip of the sleeve must be seated firmly on the bottom Timken race. The split mandrel must be used in this configuration with the lip or shoulder of the sleeves facing towards the bottom of the arbor. With both sleeves sitting squarely on the Timken race, we insert the arbor. Ensuring that the crankcase is fully supported, we gently press the Timken outer race out. Note that this bottom race can only be pressed out from this direction. With the Timken bearing outer race in our hand, we can plainly see that it is tapered and that we're only pressing against the rim of the widest face. Turning the crankcase over, we can see the snap ring and the remaining race. To remove the second Timken bearing race, we reverse the configuration of the sleeves on our arbor so that the lip of the sleeves will now rest securely on the second race itself, but clear the snap ring. Placing our crankcase back in the press, we position the two sleeves on the rim of the second outer bearing race. Only after making sure that we have cleared the snap ring, we begin to press the remaining bearing race out. Of course, we've made sure that the crankcase itself is seated squarely on the table and that it has as much support as possible. After sliding the snap ring around in its groove so that it now covers the oil passage, we insert a pin punch through this oil passage for the Timken bearing. We tap one end of the snap ring out of its groove. Then we turn the crankcase over and tap the snap ring again so that it completely twists free of its groove, enabling us to easily pull it free from the crankcase. Moving to the right-hand case, that is the case with the cone, we locate the cam bearing just above the main pinion bearing race here. Placing the right-hand case so that the cone is sitting squarely in the press, we insert our arbor into the cam bearing and carefully press it out into the cone cavity. Note that we have previously machined this aluminum arbor so it will fit snugly into the cam bearing as well as clear the crankcase housing. Once we have our cam bearing in hand, we will discard it immediately so that we will not mistakenly reuse it. We've placed our complete crankshaft assembly in a jig, with the sprocket shaft facing up. Using an 1.5 inch hex socket, we loosen the crank nut and leave it on the end of the crank pin for now. If our crank pin was a pre-1980, we would use an 1 5/16 socket. Lifting the whole crankshaft assembly out of the jig, we drop it carefully to our side and deliver a sharp blow to the sprocket shaft flywheel rim at 90 degrees to the crank pin with a lead hammer. We have just successfully loosened the sprocket shaft flywheel. With the crankshaft back on our bench, we remove the crank pin nut, then the sprocket shaft flywheel itself. Turning the remaining flywheel over on a clean rag, we pull the crank pin out of the connecting rods. Bolting the pinion shaft flywheel firmly into our jig at the end of our lathe, we crack and remove the second crank pin nut, being extremely careful that our socket does not suddenly slip off. The distance between the crank pin and the center of the flywheel is one of the major factors that controls the maximum length of the stroke of our motor. For example, the further the crank pin is away from the center of the flywheel, the longer the stroke and more low RPM torque for the quarter mile. The closer the crank pin is to the center of the flywheel, the shorter the stroke and more high RPM torque for highway acceleration. The second controlling factor is, briefly, the actual length of our connecting rods, and this in turn is controlled by the cylinders we're intending to use. Returning to the press, we place the pinion shaft flywheel on the table with the crank pin facing down. Placing a small aluminum arbor on the crank pin, we start applying pressure, and with our free hand, catch the crank pin. With our sprocket shaft flywheel firmly bolted down in our jig, we remove the sprocket shaft nut with an 1.5-inch hex socket, as this sprocket shaft was manufactured between 1972 and 1994. Sprocket shafts manufactured between 1936 and 1972 will need an 1 3/16 socket. Resting the sprocket shaft flywheel squarely on the table in our press, we take a small aluminum arbor and place it on the end of our sprocket shaft, so as not to damage either the sprocket shaft itself or the mandrel of our press. We also prefer to avoid using any hardened metals as arbors for the same reasons. We slowly press the sprocket shaft out of the flywheel, making sure that we catch the sprocket shaft with our free hand before it hits the floor. We repeat the same procedures and techniques as we used for the sprocket shaft. With the pinion shaft flywheel firmly bolted in our jig, we remove the pinion shaft nut using an 1 3/16 hex socket. Of course, we must be wearing our safety glasses and observing all the necessary safety precautions when working with our press. Having seated our pinion shaft flywheel securely in our press, we place an aluminum arbor on the end of the pinion shaft and slowly press it out of its taper in the flywheel. Here we've laid out all the new components we need to reassemble the crankshaft. First, we need to understand how the crankshaft is lubricated. Oil is fed into the end of the pinion shaft by pressure created by the oil pump and forced down to the base of the pinion shaft and out here. Then into the side of the pinion shaft hole here, where it passes through the flywheel itself. Exiting into the crank pin hole here, the oil then enters the crank pin itself and is directed to these two ports, which feed the main roller bearing assembly for the connecting rods. Before we start to reassemble the crankshaft, we must perform one final cleaning procedure. Using compressed air, we remove any lingering traces of solvents or any other foreign matter from all the oil passages. If any of the oil passages are partially obstructed or blocked, your oil flow will be either dramatically reduced or completely stopped, causing partial or total engine failure on startup. First, we inspect our new sprocket shaft and new woodruff key for any visible defects. Under no circumstances use any old or second-hand woodruff keys in the rebuilding of your crankshaft. Secondly, we must check that our woodruff key has a snug fit in both the sprocket shaft recess and the flywheel keyway, and that the keyways, recesses, and woodruff keys are free of any burrs. With our woodruff key in position, we insert the sprocket shaft into the left-hand flywheel. Note this is a taper fit and that the shaft can only be inserted from one side. We also must make sure that all the taper surfaces are totally clean and free of any oil or residue. Once we're on the correct side of our flywheel, we line the woodruff key up with the keyway and push the sprocket shaft firmly home. Now we must apply a small amount of thread locking compound to the sprocket shaft nut. In this case, we use Loctite Code Green for permanent fittings, as this nut will not be removed until the next crankshaft rebuild. For the Loctite to be fully effective, the threads on both the sprocket shaft and the sprocket shaft nut must be totally clean and free of any grease. Immediately bolting the whole assembly back into our jig, we start to pull the sprocket shaft completely into the flywheel taper and torque the sprocket shaft nut to 400 foot-pounds. To install the pinion shaft, we must first check the woodruff key recess at the base of the pinion shaft and woodruff key itself for any visible defects. Secondly, we must check that our woodruff key fits snugly into both the pinion shaft and the right-hand flywheel keyway, and that the keyways, recesses, and the woodruff keys are free of any burrs. The sprocket shaft and pinion shaft woodruff keys are different sizes and therefore not interchangeable. Of course, we've discarded all of the old woodruff keys and are only using new woodruff keys. As with the sprocket shaft, the pinion shaft has a taper and can only be inserted from the right-hand side of the pinion shaft flywheel. The pinion shaft nut is noticeably smaller than the sprocket shaft nut and therefore not interchangeable. Now we must apply a small amount of Loctite Code Green to our pinion shaft nut. With the right-hand flywheel securely bolted in our jig, we quickly pull the pinion shaft completely into place as we torque the pinion nut to 150 foot-pounds. Taking our standard crank pin, we inspect the woodruff key recess and the woodruff key itself for any visible defects. Fitting the woodruff key into the crank pin, we line the key up with the keyway and the taper on the left-hand side of the pinion shaft flywheel. We must apply a small amount of thread-locking compound, Loctite Code Green, to our crank pin nut. With our pinion shaft flywheel bolted securely in our jig, we carefully tighten the crank pin nut until the crank pin is drawn completely into the taper. Then we torque the crank pin nut to 250 foot-pounds. Reversing our pinion shaft flywheel in our jig, we locate the 3 roller cages of the crank pin bearing. The inside diameter for all 3 cages should be within 2/10,000ths of an inch of each other. First, we place one of the small cages on the crank pin. Then we use a small amount of petroleum jelly to hold the short rollers on the end of our screwdriver as we insert them into their cage. We must also spot check with our mic that the outside diameters of all the new rollers, both short and long, are plus or minus 5/10,000ths of an inch of each other. Next, we seat the largest of the new cages on the crank pin and begin inserting the long rollers using our technique with the petroleum jelly into all the recesses provided. We double-check the diameters of all the rollers as we install them. The second and final small cage is installed exactly as the previous 2 cages. Note all 3 cages are to be round, plus or minus 2/10,000ths of an inch. Here, with the rollers side by side, we can see the only difference is in the length and that they're not interchangeable. It is very important that we always use new cages, rollers, and a new standard crank pin to ensure that we will have the correct running clearance. Once all the rollers are in place, we must clean all traces of grease from the tapered section of our crank pin. Next, we're ready for both the male and female connecting rods. The overall crank pin bearing fit and wrist pin tolerances are controlled by the bore size of their respective connecting rod bushes. We set our outside mic to 792,000ths of an inch, which is the wrist pin diameter for motors from 1903 to 1984. And for motors 1984 and later, the diameter is 791,000ths of an inch. Now we use our outside mic to calibrate the bore gauge to 792,000ths of an inch. We place the anvil of our bore gauge into the wrist pin bushing on the male connecting rod. The tolerance specified by the factory manual for the wrist pin is Evolution motors 1984 to present, 3 to 7/10,000ths of an inch. Shovel head motors up to 1983, 1.5 to 8/10,000ths of an inch. We take different readings from various positions within the bushing. This way we're able to determine 2 things: A, the roundness of the bushing, and B, the tolerance fit for our wrist pin. Now we must check the wrist pin itself. Using our outside mic again, we take several readings from the wrist pin. The final test is slipping the wrist pin into the centered bronze bush of the connecting rod and feeling how tight or loose the fit is, and if we can rock the pin side to side. The fit should be tight and firm with no lateral movement. The direction in which the female connecting rod faces is very crucial. The rear connecting rod or female rod and the front connecting rod or male rod rotate together in the crankcase in this manner, with the female rod's opening facing towards the front of the crankcase. The crank pin then dumps oil out here, and as the rotation goes through the bottom of the crankcase, oil then flies out onto the front of the wall of the crankcase. As the rotation of the crank pin continues around to the top of the crankcase, the oil collects in the back section of the female rod. Remember, back here on the rear crankcase wall, we have the scraper channel. So as oil is dumped out of the crank pin in the lower part of the front half of the crankcase, it's spread across the bottom of the motor until it reaches the scraper channel here. If the female connecting rod is installed on the crank pin incorrectly in the reverse direction facing the rear crankcase wall, oil will be dumped off right above the scraper channel and sprayed directly into the rear cylinder and cause the engine to smoke unnecessarily. Since we're using a standard crank pin of 1¼ inches, the inside diameter of both the connecting rods have to be between the tolerances specified here by our chart, giving us a tolerance of 5/10,000ths of an inch. This clearance for shovel head motors would be between 1 and 1.5 thousandths of an inch. To make the matching of the crank pin and rods simple, we use new connecting rods, but if we were using our old connecting rods, we would have to change the crank pin. There are 2 oversized crank pins available in 2 increments, 1/1000th inch blue dot to 2/1000th inch red dot. The big ends of both the female and the male connecting rods are measured with our bore gauge just as we did with the small ends of our connecting rods. If we're reusing our old connecting rods, they will have to be honed to the nearest race inside diameter as specified in our previous crank pin chart. The width of our new female rod is between 1.743 inches to 1.745 inches. Here we have a classic example of a male connecting rod that has had too much clearance and allowed the rollers to skate, causing these deep grooves and hot spots in the bearing surface. Next, we carefully slip the connecting rods over the crank pin, keeping all the rollers in place. With Evolution motors, we must make sure that the small curve at the base of the male rod is facing away from the female rod and towards the front of the crankcase. The female rod opening must face towards the front of the crankcase. Place the sprocket shaft flywheel in position on the crank pin. We must be sure that all tapers are absolutely free of any petroleum residue, burrs, or foreign matter. Using a flywheel clamp, we pull both flywheels firmly into alignment by tightening the nuts before we install the crank pin nut. Once we have both flywheels in position, we apply a small amount of permanent Loctite Code Green to our crank pin nut. We torque the second crank pin nut down to 250 foot-pounds with our 3-foot torque wrench. Now we check the side play of our connecting rods on the crank pin with a set of flat blade feeler gauges. The clearance between the connecting rods and the flywheel should be between 5 and 25 thousandths of an inch. We carefully seat the crankshaft securely on the centers in our truing stand. Do not over-tighten, as the crankshaft must be able to rotate freely. Slowly rotating the flywheel several times, our dial indicators have shown us that the crankshaft is out of alignment by several thousandths. In fact, it has a slight V-shape angle to its axis. Rotating the crankshaft, we locate the extreme high point. In this case, the high points are both on the crank pin side of the sprocket shaft and the pinion shaft, which means the flywheels are too close together opposite the crank pin and must be forced further apart. To remedy this type of misalignment, we make a screw-type wedge, as seen here. Taking our wedge, we insert it firmly between the flywheel rims at exactly 180 degrees to the crank pin. By slowly unscrewing the nut on the wedge with a pair of open-end wrenches, we spread the flywheels past the point of alignment by approximately 15 to 20 thousandths. The reason we pass the point of alignment is that as soon as we remove our wedge, the crank pin will try to spring back to its original position as it is under immense tension, so in fact we will have only moved the crank pin a few thousandths. After using the full adjustment of our wedge, we now find that one shaft is higher than the other. This indicates that one flywheel is slightly higher than the other. In this case, it is our pinion shaft flywheel that is higher than the sprocket shaft flywheel. To correct this particular problem, we must use a lead mallet and hit the pinion shaft flywheel here at the high spot on the rim at 90 degrees to the crank pin. We do not hit the crankshaft while it is in the truing stand. Removing the crankshaft, we gently drop it by our side and deliver a couple of quick, sharp blows with a lead mallet to the high spot on our pinion shaft flywheel. Warning: under no circumstances hit any of the flywheels with anything other than a lead or copper mallet. Returning the crankshaft to the truing stand, we check to see if we were successful in moving the pinion shaft flywheel back into alignment. We repeat the previous truing operation until our indicated runout on both the sprocket shaft and pinion shaft does not exceed 1/1000th of an inch. Now, if we have the reverse scenario where both the high points are opposite the crank pin side of the sprocket shaft and pinion shaft, this indicates that the flywheels are too far apart and must be pulled together using a large C-clamp. Again, we compress the flywheels by an extra 10 to 15 thousandths to allow for the springing action of our crank pin. We may need to repeat all three truing procedures several times until we achieve the 1/1000th of an inch runout on both the sprocket shaft and pinion shaft. If we find it impossible to true the crankshaft, we must check for the following: damaged or enlarged tapered holes in the flywheels, any petroleum residue or any foreign matter that was not successfully removed before starting the assembly, or that the surfaces are worn on both the sprocket and the pinion shafts where our dial indicators are positioned. Here we have three aftermarket crankcases for comparison. This set of Sputh cases to the right of your screen has a standard evolution deck with a spigot diameter of 3.69 inches, which will accept the stock 3.5-inch evolution cylinders. The weakest point in this style of crankcase is in the rear spigot wall next to the tappet block relief. The width of this spigot wall is 292 thousandths of an inch. Secondly, we have a set of S&S sidewinder cases which have a spigot diameter of 3.878 inches and will accept oversized cylinders up to 3.625 inches in diameter. The width of this spigot wall in this particular set of S&S cases is 201 thousandths of an inch. Next, we have another set of Sputh cases that have a spigot diameter of 4.010 inches and will accept oversized cylinders up to 3.780 inches and support a stock deck height and stud pattern, as the previous other two crankcase sets. The spigot wall thickness here is 137 thousandths of an inch. Finally, on stock crankcases, the rear spigot wall thickness is 248 thousandths of an inch. Looking from the front spigot, we find the reason why the rear spigot wall is the Achilles heel. This oil passage here is drilled on an angle back from the front spigot towards the rear spigot and feeds these two oil passages for the tappet blocks. The problem is down here where the cone is attached to the main case. This oil passage, which is terminated here by a plug, goes under this boss along the rear spigot wall and below this deck, across here to the oil pump. Due to the engine vibration, conventional cases are prone to cracking along this oil passage. This first manifests itself as a small oil leak, and it's often presumed to be a leaky gasket from the back lifter block or the oil pressure sender leaking. What's actually happening is the case is cracked here underneath the cylinder studs. When this happens, the cases are destroyed and need to be replaced as soon as possible. Selecting the side of our cam bearing with the writing on it, this is the face we must press against. We do not use the reverse side or the face with the rounded edge and no writing on it, as we will collapse and totally ruin the new cam bearing. With our case securely in our press, we place the new cam bearing squarely on its housing in the cone. Inserting our arbor, we carefully press the cam bearing in until it is flush with the case. The cam bearing can only be inserted in this manner from inside the cone. To assemble our Timken bearing, we need two new tapered outer races, two new tapered roller bearing inner races, one new snap ring, and one new spacer. The Timken bearing is assembled in the following manner. We place an outer race over an inner race, then we place the snap ring on top of it, followed by a spacer, then the second outer race, and finally the second inner race. Now we bear down very firmly on the top inner race. The snap ring should move backwards and forwards freely to give us a positive clearance. Using a flat blade feeler gauge, we pass it through the snap ring and the top outer race. At present, the clearance is 8 thousandths. Ideally, we need 4 thousandths. Using our outside mic, we establish that our current spacer thickness is 119 thousandths. Therefore, we need to drop 4 thousandths, bringing the preferred spacer thickness to 115 thousandths. The spacers are supplied in varying thicknesses specifically for this purpose, as shown by this chart. We will have to sort through all the available spacers and select the spacer that will give us our required Timken bearing running clearance. Once we have found the desired spacer, we install it and proceed to confirm the running clearance. Using our feeler gauges, we find that 3 thousandths is a slightly loose fit. Moving to 4 thousandths, we find this is a firm fit, and that the Timken bearing running clearance is set correctly at 4 thousandths. Before we install our new snap ring, we must be conscious of the main oil feed passage for the Timken bearing here. The snap ring must not cover or partially obstruct this oil passage in any way. With this in mind, we insert the base of our new snap ring into the Timken bearing housing. Then, pushing the snap ring towards its groove, we use a pin punch and gently tap both ends of the snap ring into the groove. Rolling the case over, we tap the rear of the snap ring carefully into the groove. Then we double-check that our oil passage is unobstructed by the snap ring and that the snap ring itself is securely in its groove. Using our outside micrometer, we measure the outside diameter of the new Timken bearing outer races in several places around the circumference on both races. In this case, there is only a slight variance of 1 thousandths between the two outer race diameters. Now we use our micrometer to calibrate our bore gauge to match the outside diameter of our first Timken bearing outer race, inserting our bore gauge into the right-hand side Timken bearing housing. We take several readings to check that the housing is round and that we have the correct clearance for our press fit. Next, we select a socket to act as an arbor. The outside diameter of the socket must clear the housing but sit securely on the thin lip of our outer race. First, we apply a thin coating of grease to the housing. This layer of grease will act as a lubricant and help the outer race to slide into position. We place the outer race squarely on the housing with the taper or the thin lip facing up. The rear or wide side of the race must face the snap ring. Seating our socket squarely on the outer race, we proceed to press it into the Timken bearing housing until it is firmly up against the snap ring. The second outer race is installed from the other side or right-hand side of this crankcase using the exact same procedures we used for the first outer race. The grease will also prevent any unnecessary damage to the Timken bearing housing itself. Again, we must ensure that the taper or thin lip of the outer race is facing up, and then we press it firmly up against the snap ring. First, we must install the pilot assembly into the sprocket shaft crankcase. Taking the pilot and one of the used inner races from our old Timken bearing, we slip it over the end of our pilot and insert it into the crankcase so that the pilot will face towards the pinion shaft case. Rotating the sprocket shaft crankcase, we place the second inner race onto the pilot. Then, taking the lock nut, we screw it onto the end of the pilot until we cannot tighten it anymore. Under no circumstances use the new Timken bearing inner races to install the pilot. Here we have the whole lapping tool complete with the pilot assembly. The purpose of the pilot assembly is to allow the lapping tool to align itself with the sprocket shaft main bearing. The reason we do not use the new Timken bearing inner races is that they will be contaminated with the lapping compound, rendering them unusable. Next, we bolt the two crankcase halves securely together. We do not apply any sealant to the cases at this stage, as we're only line lapping the main bearings, and we must disassemble the cases to install the crankshaft later. Then we fasten the whole crankcase into a rigid engine stand. Before we start lapping, we calibrate our bore gauge to the pinion shaft bearings and inspect the pinion shaft bearing housing to confirm whether or not we're within the factory specified tolerances of 2 10,000ths of an inch to 9 10,000ths of an inch. Using a C-wrench, we adjust the expanding mandrel on the lapping tool before we apply any lapping compound, so that there's only a slight drag on the mandrel as we rotate the lapping tool inside the pinion shaft bearing housing. It's very important that we do not adjust the mandrel in the bearing housing, as this will result in the bearing housing having a bell shape where the center of the housing is larger than either opening. We insert the lapping tool through the pinion shaft bearing housing and into its pilot. We withdraw the mandrel just enough to coat it with a fine grip lapping compound. After applying a thin, even coat of the lapping compound, we push the mandrel back into the pinion shaft bearing and begin slowly rotating the lapping tool. While rotating the lapping tool by hand, we must move it back and forth along the complete length of the adjustable mandrel in the pinion bearing housing. This technique will ensure that we do not end up with an uneven, irregular, or tapered bore in our pinion shaft bearing housing. This is a very subtle process, and it will take a while, as we're only removing a few thousandths of an inch of the inside diameter of the bearing housing. Under no circumstances do we use a machine-powered hone or lapping tool, as this will remove too much metal too quickly and leave us with an oversized or oblong pinion shaft bearing housing. At regular intervals, we remove the lapping tool and completely clean the housing and check to make sure we're still within the factory-specified tolerance. The lapping is complete when the bearing surface of the pinion shaft housing is one uniform dull texture. This indicates that our bore is in alignment with the sprocket shaft main bearing. Finally, we measure the bore diameter of the pinion shaft bearing housing, which is now 1.7509 inches, and check that the bore of the pinion shaft bearing housing is consistently round. Taking our factory sprocket shaft bearing installation tool, we assemble it in this configuration to install the two inner races or cones of our Timken bearing onto our sprocket shaft. First, we apply a thin coating of grease to our sprocket shaft. Note we do not use any of the outer races, inner races, or snap rings from our old Timken bearing assembly. At this point, we slide the first new inner race over the sprocket shaft with the small end of the taper facing up. With the first inner race sitting squarely on our sprocket shaft, we place the bearing installation tool onto the shaft as well. Once we have the bearing installation tool in position, we start to press the inner race down until it is firmly against the shoulder or flange at the base of the sprocket shaft. Of course, we've mic'd both our sprocket shaft bearing surface diameter and the internal bores of the new inner races of our Timken bearing to ensure we have the correct tolerance of 15 to 5 10,000ths of an inch to give us the correct press fit. Next, we slip our 115 thousandths of an inch spacer over the sprocket shaft and seat it on top of the first inner race. Then, lightly greasing the remaining bearing surface in the first inner race, we place the left-hand crankcase over the sprocket shaft. Now we insert the second Timken bearing inner race, seating it squarely on the sprocket shaft, this time with the small end of the taper facing in towards the crankshaft. Securely placing our factory bearing installation tool onto the sprocket shaft, we press the second inner race in till it's firmly up against the thrust ring and the first inner race to ensure that we will have the correct running clearance of 4 thousandths of an inch. While we're pressing the second inner race into position, we need to ensure that the connecting rods are in the correct position so they'll not foul the crankcase. Now the Timken bearing is completely assembled. Before we can install the pinion bearing assembly, we must first match the pinion bearings themselves to the pinion bearing race in the left-hand crankcase, and then the pinion shaft itself to the pinion bearings as per the pinion shaft bearing chart in the Harley Davidson service manual. The running clearance we use for this pinion bearing assembly is 5 to 1/10,000th of an inch. It is very important that we do not go under the minimum running clearance of 5/10,000ths of an inch, because the bearing may start skating, which will result in a lot of heat buildup and eventually bearing seizure due to heat expansion, so we prefer a slightly looser fit. In the reverse scenario, if the pinion bearing is too loose, this results in an excessively noisy bearing. The pinion shafts and the pinion bearings are available in a variety of diameters, both standard and oversize. In our case, with the bore diameter of our pinion bearing housing being 1.7509 inches and the pinion shaft diameter is 1¼ inches, we consult the pinion bearing chart and it tells us that we'll need a code blue pinion bearing. This also indicates that the pinion shaft is a code green and the crankcase is a class 2. If we were using stock cases, we would find the crankcase class code is stamped below the right-hand side spigot. We've only covered the 5-piece crankshaft. Please refer to your Harley Davidson Workshop manual for a proper bearing selection for the 3-piece crankshaft. After matching all of the components correctly, we place the first shim on our pinion shaft. Then, taking the 2 code blue pinion bearing races, we seat them on the first shim. Once the pinion bearing is in place, we position the second shim on top of the bearings themselves. To hold the whole pinion bearing assembly in place, we use our circlip pliers to install a new snap ring groove on the pinion shaft. Selecting one of the 2 smaller woodruff keys, and of course we've already inspected this woodruff key for any defects, we tap it into the bottom recess on the pinion shaft. The feel of the fit for the woodruff key must be tight and firm. Lining up the keyway, we slide the drive gear for the oil pump over the pinion shaft, pushing it home. Then, taking the spacer, we place it on the drive gear. Inserting the second small woodruff into the top of the recess of the pinion shaft, we angle the front of the woodruff key down slightly. Now we can easily slide the pinion gear over the woodruff key and onto the spacer. Finally, we install our left-hand thread lock nut to hold the whole pinion shaft assembly in place. Here we've split the cases again and are preparing them for the final assembly. First, we must remove any burrs from both crankcase halves, and then we use some acrylic thinners and remove all traces of oil and grease from both of the mating surfaces. We also take the time to double-check that both mating surfaces are in good condition and free of any indentations and scratches. Next, we apply a liberal coating of assembly lube to the pinion shaft bearings. Now we're ready to apply a thin, even layer of gasket sealant to each crankcase half. We must be careful and avoid getting any gasket sealant either in the bolt holes or especially on the inside of the crankcase, as we do not want any excess sealant to break free and contaminate our oil and possibly block any of our oil passages, which would lead to either partial or total engine failure. Carefully placing the pinion shaft case into position on the sprocket shaft case, locating dowels when we push the 2 halves together. Next, we insert all of the case bolts and torque them down to 15 to 19 foot-pounds. Remember to torque the case bolts or studs in the correct sequence as outlined in our previous video manual's engine overhaul tapes, so that the cases will be properly aligned. After zeroing our crane cam dial indicator to the pinion shaft, we slowly rotate the crankshaft to check that we are within our tolerance of 0 to 1/10,000th of an inch. We also double-check that the ball of the stem of our indicator is at 90 degrees to the pinion shaft and that the supporting arm assembly is rigid. Moving our crane cam dial indicator, we slowly rotate the crankshaft while trying to move the whole crankshaft assembly back and forth within the crankcase. The factory-specified tolerance for this in-play is 1 to 5/1000ths of an inch. We like to keep the in-play closer to 1/1000th of an inch. It is very important which direction our oil seal will face. If we have a dry clutch motor, the opening of the oil seal must face the crankshaft. Now, if we have a wet clutch motor, the oil seal opening must face towards the primary. Before we insert the spacer into our oil seal, we apply a thin film of oil to the circumference of the spacer to ensure that we do not damage our oil seal. In this case, we're building a dry clutch motor, therefore we must position the oil seal on the spacer so that it will face the crankshaft. We then carefully slip the oil seal into position on our spacer and check that the rubber section of the oil seal itself has not folded or torn itself. We take some gasket cinch to avoid any possible oil weeps or leaks between the oil seal and the crankcase and apply a generous coating around the circumference of our oil seal. Sliding both the spacer and the oil seal over the sprocket shaft, we position the oil seal so that it is squarely against the crankcase. Notice our GEM sprocket shaft oil seal installation tool is only slightly different to the sprocket shaft installation tool, and that difference is the shape of the arbor required for each task. Screwing the GEM sprocket shaft oil seal installation tool onto our sprocket shaft, we carefully press the oil seal into the crankcase until it is firmly in its housing. Under no circumstances do we reuse the old and/or second-hand sprocket shaft oil seals. If we damage the oil seal during the installation, the oil seal will start leaking immediately once the motor is operating. The leaking oil seal will allow both the engine oil and the primary oil to be contaminated by one another. So it is worth our while that we take our time with this procedure. To make sure the connecting rods are not bent to the left or right or twisted front to back, we insert our specially ground dowel pin with a diameter of 792 thousandths of an inch into the connecting rod in question. Pushing the connecting rod down until it's resting on the rear spigot surface, we take a thin piece of rolling paper and insert it between the dowel pin and the spigot. Applying a slight but constant pressure to the connecting rod, we pull the paper out slowly, taking note of the amount of effort or drag it requires to remove the piece of paper without tearing it from both sides of the spigot. If the rod is bent, the paper will pull free on one side and be tight on the other. Moving the connecting rod forward to the front of the spigot surface, we repeat this procedure. The drag should be equal on both sides here as well. Rotating the flywheels in the opposite direction until our dowel pin is again resting on our spigot, we repeat the procedure once more on both the front and rear of the spigot. If the drag on our paper is uneven or loose in any of these four positions, this indicates that this particular connecting rod is twisted, and we would replace this or both offending connecting rods. First, we will require our degree wheel and a pointer which we have fabricated out of a piece of welding rod. Next, we slip the degree wheel onto the sprocket shaft. Secondly, we've set up a crane cam's dial indicator on our front piston. To do this, we have temporarily seated a cylinder on the front spigot without any gaskets or cylinder studs. We have also placed a wrist pin and piston without any circlips or rings on the front connecting rod. By assembling the front cylinder like this, it will allow the piston to move freely in the bore without doing any damage to the cylinder or waste any gaskets or circlips. The dial indicator will help us to find the uppermost travel of the front piston. Bolting the pointer to the crankcase at the 1 o'clock position, we line up the 0 degrees or top dead center mark of the degree wheel so that it corresponds with the pointer. Taking our metal oil breather gear, we insert it into the cone assembly. We must ensure that the pinion gear timing mark is aligned with its corresponding mark on the cam and that the breather pinion gear is also correctly aligned with the cam. Slowly rotating the crankshaft, we watch the breather tube window through the rear tappet block hole. We stop rotating the crankshaft when the breather gear begins to open and check the timing on our degree wheel. In this case, our breather gear is open at 1 degree before top dead center. We continue rotating the crankshaft until the breather gear starts to close. At this point, we stop rotating and return to the sprocket shaft side of our motor to find the corresponding position on our degree wheel, which in our case is 55 degrees after bottom dead center and is within the normal factory parameters for a stock 80 cubic inch motor. As we're building a Sputh 104 cubic inch motor, we need to enlarge the breather gear window. To this end, we apply some blue dicom to each side of our breather gear so that we can mark the new positions for the breather window. With our breather gear back in the crankcase, we set the degree wheel to the new opening timing of 2 degrees before top dead center. Now from the cone side of our motor, we scribe a straight line for the new opening position on the breather gear using the crankcase itself as a guide. Next, we locate 75 degrees after bottom dead center on our degree wheel. Returning to the cone side of our motor, we insert our scribe and locate the bottom side of the crankcase breather window and scribe another line on our breather gear for the new closing position. Rather than experiment with the expensive metal breather gear, we will substitute a plastic breather gear, which is 1/4 of the cost of the metal breather gear. We have used the above techniques to mark our new opening and closing positions as shown here. Locking the plastic breather gear into a small engineer's vise, we use a pneumatic die grinder to machine the breather gear. You must be wearing your safety glasses to proceed any further. Holding our die grinder firmly, we take our time and, with very deliberate movements, carefully remove the unwanted material, making sure that we do not go below our scribed lines. Once the bulk of the unwanted material is removed, we must make sure that the new window position is parallel to our scribed lines. The tolerance we're working with is 30 thousandths of an inch or 3 degrees. If we go outside this tolerance, our motor will suffer the following symptoms: poor oil scavenging from the flywheel cavity, a dramatic increase in air pressure in the crankcase causing gaskets and seals to leak, and possible blow-by past the piston rings causing the motor to burn oil excessively. Using a fine file, we clean up the new breather gear and make sure that the new enlarged breather window is square, and fine-tune the openings so that they correspond closely with our scribed lines. Taking a triangular blade, we meticulously deburr the breather gear window, as we do not want any foreign matter contaminating our oil or possibly seizing the oil pump and or damage any of our bearing surfaces or bearings. After we have successfully tested the plastic breather gear and our motor, we then pop the filter screen out of the metal breather gear. We machine it in exactly the same manner and to the same position as we did with the plastic breather gear. Then we reinstall the breather gear screen and replace the entire metal breather gear back into our motor. Now, if we would rather machine the oil breather gear window in our crankcase, we would first apply some blue Dycomb to the top and bottom of the window and the bore of the breather gear housing. Next, we must work out how much metal we have to remove from each side of the openings. First, we've established with the aid of our degree wheel that the current breather window timing is 1 degree before top dead center and 55 degrees after bottom dead center. The new timing specified by Sputh Engineering for their 104 cubic inch motor has the breather window opening at 2 degrees before top dead center and closing at 75 degrees after bottom dead center. This means we have to move the opening side of the breather window tube up 1 degree, and the closing side of the window has to move down 20 degrees. The outside diameter of our breather gear is 1.125. Now, to calculate the outside circumference of the breather tube, we multiply its outside diameter, 1.125, by pi, giving us a circumference of 3.534. To find the equivalent of 1 degree in a linear measurement on the outside circumference of our breather tube, we divide the circumference of our breather tube by 360, giving us 0.0098 inches. This means 1 degree on the circumference of our breather tube is equivalent to 0.0098 inches. For ease of quick calculation, we will approximate that 1 degree is equivalent to 10 thousandths of an inch. We're able to do this because we have a tolerance of 3 degrees, which is equivalent to 0.0294 inches, so our small approximation will not have any significant difference. We said earlier that we had to move the breather window opening up by 1 degree and the closing down 20 degrees. Now we can translate this into linear measurements of 1 degree being equal to 10 thousandths and 20 degrees being equal to 200 thousandths, or approximately 13/64. Taking a 6-inch rule, we place it squarely against the rear shoulder and the breather gear housing, and at 13/64 below the current closing window, scribe a straight line. In this case, we do not have to alter the opening of our breather tube window, as it is well within our tolerance of 30 thousandths of an inch. Carefully inserting our pneumatic die grinder into the breather window, we start to remove the unwanted metal with slow and deliberate movements. We do not want to damage the bearing surface inside the breather gear housing, therefore we must be very conscious just how far we insert the die grinder. We try to maintain the existing angle of the breather window as we are machining. We must frequently check our progress from inside the bore so that we do not machine past our scribed line. If we do machine past our line and take the window completely outside our 30 thousandths of an inch tolerance, the damage is irreversible and the crankcase is now useless. The type of burr or bit that we use in our die grinder must have coarse flutes, as seen here, so that the aluminum does not clog the burr and reduce its cutting efficiency. Once we've reached our line, we try to make the window as parallel to it as possible with our die grinder. We use a bastard file to make our window completely square and parallel to our line. Then we use a piece of very fine emery paper to remove all the burrs on the inside of the window. To confirm that we have indeed removed all the burrs, we run our finger lightly over the inside of the window. Replacing our metal breather gear back into its housing, we use our degree wheel to confirm that we have the oil breather window opening at 2 degrees before top dead center and closing at 75 degrees after bottom dead center. We must also check that the breather gear is rotating freely and that the bore is completely free from all foreign matter and obstructions. The only difference between the S&S oil pump and the new factory oil pump is that the factory has moved this bolt hole across by approximately 1/8 of an inch. This is clearly demonstrated when we place an old-style gasket on both oil pumps. Rotating both oil pumps, we can see at first glance that the S&S oil pump has a more complex network of oil passages. Once again, turning the oil pumps over to the front side, we place the respective front cover plates onto both the oil pumps. Here we can immediately see some very distinctive differences. First, on the S&S oil pump, we can see that we have a wide variety of options that we can use to suit our particular motor, such as we can take the oil out here at the base of the oil pump, whereas the new stock oil pump basically has only one oil outlet for the oil filter and the oil return from the oil tank. One bonus is that both the smaller or feed gears and the larger or scavenger gears are the same size in both pumps and therefore interchangeable. In our oil pump, oil enters here in the feed port and is pulled around by the feed gears and pushed up and through this port in the body of the oil pump. To follow the flow of the oil, we turn to the other side of our oil pump. The oil continues up and lifts the check valve. The sole purpose of the check valve is to stop oil flowing back into the crankcase when the motor is not in use. From the check valve, the oil is first directed across to here and up to the top end of our motor. Once the oil pressure has reached 3 pounds, it will lift the relief valve, allowing oil to flow to our bottom end. The sole purpose of the relief valve is to direct the total oil flow to the top end of our motor while the oil pressure is below 3 pounds. The excess oil from the relief valve is routed through the oil pump body and comes out here and is circulated back through the front cover and reintroduced to the pressure pump here. Once the oil has traveled through the motor, it's picked up from the cam cover here, and the scavenging gears force the oil through this small passage, which is routed through the pump body and comes out here on the front side of our oil pump and exits through the top cover. First, we must weigh the reciprocating mass. We take the front piston, which has the wrist pin already in it, and place it on the scales. Next, we take the rear piston, complete with wrist pin, and seat it on top of the front piston. The rear piston is easily identified by this large notch in the skirt of the piston. We have previously weighed both pistons with their respective wrist pins and circlips individually, and the weight difference is 3.5 grams. Continuing, we place the retaining circlips for each wrist pin on our rear piston. In our particular case, we're using 4 circlips to retain each wrist pin. Of course, we've previously zeroed our scales to ensure that we get accurate measurements. We follow the circlips with 4 oil rails, or scrapers, then 2 oil expanding rings, 2 second compression rings, and the top 2 compression rings. It is very important that we record all these measurements, as we will need to recall accurately the individual weights for all the components in our calculations later. The total weight of this part of our reciprocating mass is 1,041 grams. Now we weigh the first part of our rotating mass. Placing the crank pin in the center of our scales, we must exchange our 1,000 gram counterweight for a 500 gram counterweight before proceeding any further. Next, we place the 2 crank pin nuts on our scales, followed by the woodruff key for the crank pin, then the 3 cages for the crank pin bearing, plus all the rollers for the crank pin bearing. We have determined that the plastic bag containing all the rollers weighs 0.5 grams and must be deducted from the total weight of this assembly. The total weight of the first section of our rotating mass is 713.5 grams. Before we proceed any further, we must weigh the stand we are going to use to suspend the respective ends of our connecting rods during the following procedures. To get an accurate reading, we must ensure that our stand is in the center of our scales. In this case, our stand weighs 688.3 grams. Next, we're going to weigh the reciprocating mass content of our male connecting rod. To do this, we must suspend the small end of our male connecting rod from the stand sitting in the center of our scales. We also suspend the big end of our male connecting rod from a height gauge seated on the bench. The male connecting rod must be level so as to ensure that we get an accurate reading. The combined weight of the small end of our male connecting rod and the stand is 940 grams. Secondly, to measure the rotating mass content of our male connecting rod, we place the big end of our connecting rod on our scales. Once again, we adjust the height stand so that our connecting rod is level. The combined weight of the big end of our male connecting rod and the stand is 1,050.5 grams. Next, we place the whole male connecting rod in the center of our scales. The total weight of our male connecting rod is 615 grams. Now, to get the true weight of the small end of our male connecting rod, we must subtract the weight of our stand, which is 688.3 grams, from our previous combined measurement of 940 grams, leaving us with 251.7 grams, which is the reciprocating mass content of our male connecting rod. Next, we must also subtract the weight of our stand, 688.3 grams, from the combined weight of the big end of our male connecting rod, 1,050.5 grams, leaving us with 362.2 grams, which is the rotating mass content of our male connecting rod. To double-check our measurements, the combined weight of the reciprocating mass content and the rotating mass content of our male rod, which is 613.9 grams, should be within a couple of grams of the total weight of the male connecting rod, which in our case is 615 grams. We use exactly the same procedures and techniques to obtain the reciprocating mass content and rotating mass content of our female connecting rod. We must also ensure that the string is located in the center of the respective ends of our connecting rods, and that it is also parallel to each of the stands so as to ensure accurate measurements. The reciprocating mass content of our female connecting rod is 259.2 grams, and the rotating mass content is 515.2 grams. Now we can calculate the total reciprocating mass content of our motor by adding the following: the total weight of our pistons, wrist pins, retaining circlips, and rings, 1,041 grams. The reciprocating mass, the small end of our male connecting rod, 251.7 grams. The reciprocating mass, the small end of our female connecting rod, 259.2 grams. The total reciprocating mass weight, 1,551.9 grams. Next, we calculate the total rotating mass content of our motor by adding the following: the total weight of our crank pin, both crank pin nuts, woodruff key, the 3 crank pin bearing cages, and all the rollers, 713.5 grams. The rotating mass, the big end of our male connecting rod, 362.2 grams. The rotating mass, the big end of our female connecting rod, 515.2 grams. The total rotating mass weight, 1,590.9 grams. Now, to calculate the weight of the counterweight we must use to balance our flywheels, we multiply the total reciprocating mass by 60%, giving us 931.14 grams. The total reciprocating mass, 1,551.9 grams, times 0.6 equals 931.14 grams. Then, taking this figure of 931.14 grams, we add it to the total rotating mass, which gives us 2,522.04 grams. The total rotating mass, 1,590.90 grams, plus 931.14 grams equals 2,522.04 grams. Now we multiply 2,522.04 grams by 50%, which will give us the correct counterweight. 2,522.04 grams times 0.5, total counterweight 1,261.02 grams for our particular motor. We round off the 1,261.02 grams to 1,261 grams for our counterweight. Next, we place our counterweight assembly in the center of our scales and keep adding shims until we reach the required weight of the 1,261 grams. Now we assemble the counterweight by first inserting the shims over the threaded mandrel. Next, we take the tapered spacer, and with the big end of the spacer facing the shims, we screw the spacer onto the threaded mandrel until it is holding the shims very firmly. Remembering that the tapered spacer will only fit from one side of the flywheel, we turn the flywheel and insert the tapered spacer into the large opening of the flywheel taper. Again rotating the flywheel, we also bolt the second half of our counterweight assembly firmly into our tapered spacer, thus locking the entire counterweight assembly securely in our flywheel. Taking our balancing shaft, we must mount it into the pinion shaft taper of our flywheel. In our case, we will not require the additional 2 large tapers, so we remove them completely. Inserting our balancing shaft into the pinion shaft taper, we rotate the flywheel and screw the locking nut firmly up against the left-hand side of the flywheel. We use a spirit level to confirm that both sides of our balancing stand are level, so as to ensure the accuracy of our balancing. Placing our right-hand flywheel complete with the counterweight and the balancing bar onto our stand, we let the flywheel settle, as the heaviest side of the flywheel will always gravitate to the base of our stand. Once our flywheel has settled, we mark the heaviest point with our marking pin. This is where we will have to remove metal in an effort to balance our flywheel. To obtain a visual representation of how much metal we have to remove from our flywheel, we place the 2 crank pin nuts on our counterweight and rotate the flywheel past its current balancing point. In this case, the additional weight of the crank pin nuts on our counterweight has significantly slowed the rocking motion of our flywheel as it tries to settle. This indicates that we're very close to the point of balance with this flywheel. The further our flywheel is out of balance, the more violent or radical the rocking movement is as our flywheel tries to settle. Centering the heaviest point we had marked on the rim of our flywheel underneath our 3/8-inch drill, we proceed to carefully remove the excess metal from the rim. Note that we have set our depth gauge for 1/2 inch so as not to remove too much metal too quickly. In our case, we have elected to drill 3 holes to remove the unwanted metal. We also frequently return our flywheel to the balancing stand to carefully monitor our progress. Our flywheel movement has dramatically slowed, and it almost stays in any position we leave it in. As the flywheel still tries to gravitate to the base of our stand, this indicates the flywheel is not yet balanced, but is very close, and that we must be extremely cautious in removing the last couple of grams of metal. Making a slight adjustment to our depth gauge allows us to completely control the removal of the final few grams of metal from our flywheel. Our flywheel is balanced when it will remain in any position that we place it in on our balancing stand. That is to say, it will not gravitate at all. If we remove too much metal and go past our point of balance, we must again find a new heavy point for our flywheel and repeat the above procedures. We try to avoid this as much as possible, as we do not want to reduce the overall mass of our flywheels unnecessarily. We balance the sprocket shaft or left-hand side of the flywheel using the exact same techniques and procedures as we just used with the pinion shaft or right-hand side flywheel. Now, if we're balancing a late model 3-piece crankshaft, we would use the exact same procedures that we have just used with the 5-piece crankshaft, the only exception being the style of balancing bar. As the pinion shaft and sprocket shaft are part of their respective flywheels, the new style of balancing bar screws over the end of each shaft. Then we place the balancing bar and pinion shaft flywheel into our stand and continue as we did with the older style 5-piece crankshaft. This completes the bottom-end reassembly and balancing of a stock 1340cc Harley Davidson V-twin motor.
We at Video Manuals wish to gratefully acknowledge and thank Mr. Alan Sputh and his wonderful crew for allowing us to use their facility and products in providing the technical information used in this video.